Hi, welcome to Modern Optimization Methods. I'm Qingna Li from Beijing Institute of Technology. Today we will introduce the first part of Chapter 4, the Trust Region Methods. Now, this is the outline of the methods. We will start with the main idea of trust region methods, then go through the algorithms of trust region methods. In the next, we will discuss how to solve the subproblem. Finally, we discuss the convergence of trust region methods. Now, let's start with the first part of Chapter 4, the main idea of trust region methods. It includes three parts. One is the size of trust region, then the model function, finally the step. Now, let's take a look at the rough idea of trust region methods. So as we mentioned before, the trust region methods works actually in the following. We first choose a circle or choose a region called a trust region. Then within this trust region, we try to find a minimizer. So whose minimizer? The model function's minimizer. And after that, we jump directly to that minimizer. This will be the trust region methods. So from the statement above, we can find that there are actually many key points in the trust region methods. Now, I summarize the key points in the following. So the first one is the size of trust region. So how big or how large the region I will choose, it is a very key factor to the methods. The second one is what kind of approximation function I will use. We call it the quadratic model function because naturally we will use the quadratic function. So we refer it to as quadratic model function. And the third factor is the step pk. The step means that I jump from the current iteration directly to the next iteration. So the difference between the two iterations will be called a step. In contrast, for line search method, we first determine a direction, then we determine a step length. So the direction multiplied by the step length will be the step here. So the idea of trust region methods is actually totally different from the line search methods. Now, let's first take a look at the first factor, the size of trust region. So why it is important? So think about the situation like this. If we have a very small trust region, for example, in two-dimensional space, we draw a very small circle around the current iteration, then what kind of influence do we have? So you may probably find that if I draw a very small circle around the current iteration, then I cannot move very far from the current iteration. So this will slow down the process of the iteration. Therefore, we cannot afford that the trust region to be too small. So what's the effect if we choose a very large trust region? So the very large trust region, of course, will not prevent our process to the final accumulation point. However, if the trust region is too large, then recall that we need to approximate our function value within this trust region. So this will make our approximation a great error. All right? So we need to balance the trust region size from small to big, and we need to choose a proper one. So that's why it is important for the trust region size. Now, how do we define the size of trust region? So we do have to find some rules to measure whether it is good. So the measurement is actually we use the previous iteration. Okay, so suppose we are standing at the current iteration and we have some approximation at the moment, so we can use the approximation now to estimate what will happen next for the trust region iteration. Okay, so if the performance in the previous iteration is very good, it means that the trust region at the moment is very good. So we may enlarge a little bit in the next iteration. And if the performance of the current iteration is not that good, it means that there may be not a very good trust region size. So we have to shrink our trust region size and we repeat the process again in order to get a very good approximation. So this is the rough idea for the radius of the trust region. Now, let me show you a figure to demonstrate the difference of trust region method as well as the line search methods. So if you look at the figure here, and actually we are standing at the center of this circle, this is the current iteration, and we got a trust region here, which is the big circle, right? Now, the line here are actually the contours of function f. And the dotted ellipsoid here are the contours of model function. So model function is the approximation of the function values. So in the trust region methods, we are looking for the minimizer of model function within the trust region. So remember that we only can move inside of the trust region. So within this trust region, the minimizer we can get is this point. Okay, so we jump here. However, compared to the trust region, the line search will look for the minimizer of this gradient. All right, so it actually moves along the steepest descent direction here. Okay, so you can see that there are differences between the two directions. The line search method is actually pointing out directly to the minimizer here, so it will move along this direction. So there are differences between the two, and the idea is also different. Now, let's take a look at the second key factor, the model function. As we mentioned before, model function is the approximation of the original function within a reasonable region, right? So what kind of form we can choose for the model function? So normally, we will choose the quadratic function to do the model function. So the intuition is that if we do Taylor's expansion around xk, and we can get the second order expansion here, and we replace the Hessian function by a matrix bk. Okay, so bk is an approximation of Hessian matrix, and this will become the model function. All right. We require that bk to be symmetric, and moreover, we must guarantee that the difference between the two functions must be the high order of the norm of p. Otherwise, we may get large errors, and that's why we cannot make the trust region size too large, because if this size is too large, then the error will be large as well. So this is the key fact. Second, the model function. Now, in each step, we need to solve the model function because we are looking for the minimizer of model functions instead. Moreover, we have a trust region restrictions. So we require that the step cannot be too large. It should be within a trust region size. Okay, so delta is the trust region radius. The length of P must be not exceed the size of delta. Here, another notation is that we use the norm to measure the length of this vector. And the natural norm is the Euclidean norm, which is very often used. Of course, we can choose other norms. We will talk about this later. And as you can see that if we drop the trust region restrictions, we can directly solve the solution as bk inverse multiplied by gk. In other words, if the length of this direction is smaller than or equal to the radius here, then we can automatically get the trust region solution, which is this one. In this case, it means that the unconstrained minimization subproblem coincides with the trust region subproblem. However, if the length of this vector exceeds the radius, then we have to solve the trust region problem. And it will be a complicated subproblem. We will discuss this later for more details. Now let's make a brief summary about this part. In this part, we mainly introduce the main idea of trust region methods, including 3 key factors and why they are important in the method and how we deal with them. So we stop here and see you next time.